Imagine this. In just a few years, we may finally know whether our solar system is one of billions or one in a billion. Right now, we know two big things. Almost all stars have planets. Planetary systems are common. Our solar system looks weird compared to most of them. We've never seen another system quite like ours, especially one key combination: a sun-like star with both an Earth-like planet in the habitable zone and a Jupiter-like giant further out. How many of those have we confirmed so far? Zero. Not a single one. That's a problem because some scientists think Jupiter may have been crucial for life on Earth, shielding us from comets and asteroids, shaping the early solar system, and stabilizing conditions long enough for life to thrive. So the big question is, are solar systems like ours incredibly rare, or have we just been blind to them? And to answer that, we need to understand how we've been looking for planets and how that's about to change. 1. Why we care about exoplanets in the first place. We only know one planet with life, Earth. So, naturally, we get excited about Earth-sized planets at the right distance from their star for liquid water, around sun-like stars. We call this the habitable zone idea. Not too hot, not too cold. Thanks to recent missions, we now know there are lots of Earth-mass planets in habitable zones, and many of them orbit stars roughly like the Sun. Some estimates suggest there could be around 11 billion Earth-like planets around Sun-like stars in the Milky Way. That sounds like good news for life, but maybe that's not the full story. Maybe the architecture of the whole planetary system matters. Maybe you need an Earth in the right place and a big outer planet like Jupiter acting as a gravitational bodyguard. If that's true, then finding solar system lookalikes becomes one of the most important questions in astronomy. And so far, we haven't found any. 2. The first exoplanet discoveries. Nothing like home. Planets are incredibly hard to see directly. They don't shine by themselves, they just reflect starlight and they're lost in the glare of their stars. So, astronomers mostly detect them indirectly by watching what planets do to their stars. 1992, the first exoplanets around a pulsar? The very first confirmed exoplanets weren't like our solar system at all. They orbited a millisecond pulsar, the collapsed corpse of a massive star, a neutron star spinning about 160 times per second. Its intense magnetic fields send beams of radiation sweeping across space with astonishing regularity, better than an atomic clock. But astronomers noticed tiny timing variations in those pulses. That tiny wobble in timing revealed the gravity of two planets, later joined by a third. It was a stunning discovery, but nothing like a normal star with normal planets, and definitely nothing like our Sun-Earth-Jupiter setup. 3. The Doppler or radio velocity method. Hot giants up close. Next came the Doppler or radio velocity method, which dominated the 1990s and 2000s. Here's the key idea. Planets don't just orbit stars. Stars and planets orbit a shared center of mass, called the barycenter. Because stars are so massive, the barycenter is usually inside the star, but not at its exact center. This makes the star wobble very slightly as planets tug on it. If that star is moving toward or away from us as it wobbles, its light shifts. Moving toward us, wavelengths compressed, blue shifted. Moving away, stretched, red shifted. By measuring tiny shifts in stellar spectra, astronomers can see that wobble and infer the presence of planets. Early on, the telescopes and spectrometers were most sensitive to very massive planets orbiting very close to their stars, completing orbits in just days or weeks. Result, we found lots of hot Jupiters, gas giants hugging their stars, spinning around in tight, blistering orbits. Impressive, but again, nothing like home. No Earths, no outer Jupiters, just strange inner giants. Even as instruments like Keck Hi-Res and HARPS improved and found smaller and cooler planets, the majority of what we saw still didn't look like our solar system. 4. Kepler changes everything, the transit method. The game completely changed in 2009 with NASA's Kepler Space Telescope. It used a different trick, the transit method. It stared continuously at about 150,000 stars in a small patch of sky. Whenever a planet passed in front of its star from our line of sight, the star's brightness dipped slightly. Repeating regular dips, a planet is orbiting. Kepler watched that patch of sky for around 4 years. If a planet passed in front of its star at least 3 times during that period, astronomers could estimate its orbital period, its size, from how much light it blocked. This led to an explosion of discoveries, hundreds of new exoplanets per year. For the first time, the method was sensitive enough to find Earth-sized planets, inhabitable zones, especially around small, cool stars like red dwarfs, but also some around sun-like stars. Based on Kepler's statistics and correcting for the planets it couldn't see, astronomers inferred that there could be billions of Earth-sized planets in habitable zones around sun-like stars in our galaxy alone. That sounds like good news for life. But maybe that's not the full story. Maybe the architecture of the whole planetary system matters. Maybe you need an Earth in the right place and a big outer planet like Jupiter acting as a gravitational bodyguard. If that's true, then finding solar system lookalikes becomes one of the most important questions in astronomy. And so far, we haven't found any. 5. Peas in a pod. Most planetary systems aren't like ours. Kepler and radio velocity surveys revealed a pattern. Planets in the same system tend to be similar in size, like peas in a pod. Examples are TRAPPIST-1, 7 roughly Earth-mass planets tightly packed around a red dwarf. Many other systems, chains of super-Earths or mini-Neptunes close to their stars. What we don't commonly see is a set of small, rocky inner planets followed by large gas giants much further out, which is exactly what our solar system looks like. So this raises the question, why didn't our solar system form as peas in a pod? One leading idea is the Grant-Tack hypothesis. Early on, Jupiter may have migrated inward, toward the Sun. On its way, it disrupted or destroyed larger forming worlds in the inner solar system. Later, interactions, possibly with Saturn or other dynamics, caused Jupiter to migrate back outward. The inner solar system then had to rebuild itself from what was left, forming the smaller rocky planets we see today. If events like that are rare, maybe requiring specific chain reactions or even encounters with other stars, then our configuration might be unusually rare. But right now, we don't know how rare. Why? Because we're still missing a crucial piece of data. 6. The blind spot. Jupiter's far from their stars. You might think big planets like Jupiter are easy to detect. They're massive. But the problem is, Jupiter has a 12-year orbit. Kepler only watched each star for about 4 years. To confidently detect a planet by transits, you want at least 3 transits. So, Kepler could maybe detect a planet like Mars, but not a full exo-Jupiter at 5 AU with the 12-year year. There simply wasn't enough time. The radio velocity method is also limited by time. It can detect Jupiter-like planets if it watches long enough. But radio velocity searches are done on thousands of stars, not hundreds of thousands. It's not a fast way to do a large statistical census of outer gas giants. We could keep doing transits and Doppler measurements for decades, waiting for long-orbit planets to reveal themselves, but that's slow. So, astronomers turn to a third method, one that works best for planets with big, wide orbits. 7. Astrometry. Watching stars literally wobble in the sky. Instead of measuring the color shift of a star, radial velocity, or the minute dimming during a transit, astrometry tries to measure the actual position of a star on the sky with extreme precision over time. Remember, star plus planet orbit their barycenter. The more massive the planet and the farther it is from the star, the farther away that barycenter is from the star's center. This makes the stars wobble on the sky larger for planets in wide orbits. So unlike transits and Doppler, astrometry is more sensitive to big planets in large orbits, exactly what we want for Jupiter analogs. And it also doesn't care about the system's orientation. You don't need a perfect edge-on alignment. The challenge is, the wobble is tiny. Detecting it requires staggering precision. Astrometry has been used in the past to detect stellar companions. In 1844, astronomers inferred the white dwarf Sirius B from Sirius's wobble. Similar methods revealed other binary stars, including systems with black holes and neutron stars. But doing this for planets is much harder. The wobble is smaller. We needed a... At its heart, this video is a slow cruise through the strangest corners of the cosmos. From burping black holes and burning ice planets to galaxy-spanning voids and possible bruises from parallel universes, using each bizarre object as an excuse to ask a bigger question. Where does our universe end? And what might lie beyond its walls? It blends real astrophysics, voids, dark matter halos, CMB cold spots, rogue planets, with speculative ideas, multiverse, brains, white holes, in a light, story-like tone that always circles back to, we don't know yet, but it's beautiful to wonder. Chapter-style outline you can reuse. You can turn this into a long-form video with chapters like, the Milky Way isn't as quiet as it looks, Sagittarius A** leaking jets, Fermi bubbles and new gas bubbles near the galactic center, the Milky Way's warped, twisted disk and tilted dark matter halo. Extreme objects, the universe on hard mode, Black Widow pulsars and nuclear pasta, glass rain exoplanets, burning ice worlds and diamond planets, rogue planets with titanic magnetic fields and auroras, invisible storms, radiation, gas, and galactic fire, hot gas halos around the Milky Way and superheated atmospheres, hydrogen rain clouds feeding star formation, solar terminator tsunamis and weird neutron star infrared streams, cosmic architecture, walls, filaments, and voids, the South Pole Wall in Hercules' Corona Borealis Great Wall, quasar groups as beacons tracing massive structures, cosmic webs versus enormous underdense voids, the local hole and the cosmic void problem, Kuiper belt oddities, Planet 9 hints, Hubble tension and the idea that we live inside a large underdensity, the local hole and what it might mean for life and habitability, cold spots in parallel universes, maybe, CMB cold spot and supervoid hypotheses, the great void and the idea of a multiverse bruise, why it's so hard to prove or disprove, Big Bang, inflation, and cycles, classic Big Bang versus inflation, bouncing or cyclic universes and quantum time steps, brain collisions and bubble universes, edges, walls, and the limit of what we can see, observable versus total universe, the ant on a basketball analogy, voyage to the supposed edge and the Eridon Arianis supervoid, black holes, white holes, and wormholes, supermassive versus microscopic black holes, wormholes, exotic matter, and why they probably don't work. white holes, and the Little Bang idea. Life in a mostly empty universe. Habitable worlds estimates. Life possibilities in our solar system and nearby exoplanets. Why emptiness and danger might actually be part of what makes life possible. 2. Fresh 2 to 3 minute script for your channel. Inspired by the transcript, but focused on the title, an enormous black hole far beyond the known cosmos. Calm, hypnotic, bedtime style. Tonight, I want you to imagine this. Far beyond the Milky Way, past the bright cities of galaxies we know and map, the universe turns quiet. The lights thin out. The sky grows darker. And in that darkness, something impossibly bright is hiding. A single point, so distant that its light left before Earth had oceans, now whispering into the James Webb Telescope. A flicker in the infrared. A tiny, stubborn shine. When astronomers ran the numbers, they realized what they were looking at. Not a star, not a galaxy, but the furious heart of one. An enormous black hole, millions, maybe billions of times more massive than our sun, feeding in the deep young universe at a distance that brushes the edge of what we can even see. Black holes themselves are invisible. What Webb sees is the chaos around them. Gas falling inward, spiraling into a thin, bright disk that heats to incredible temperatures. Magnetic fields twisting, snapping, flinging matter outward in jets. The space around that hole glows so intensely, it can outshine the entire galaxy that hosts it. From here, it is just a faint smudge in Webb's detectors, a few pixels against the cosmic background. But those pixels are a message from a time when the universe was young, crowded with newborn stars, still learning how to build galaxies. The strangest part is, according to our best theories, black holes this big shouldn't exist so early. They are like skyscrapers in a town that has barely learned to stack bricks. So we are left with a puzzle. Did tiny black holes grow far faster than we expected, feeding like cosmic bonfires? Did they form from the direct collapse of enormous clouds, skipping the star stage entirely? Or is there something about gravity, matter, or even the shape of the universe that we still don't understand? Look outward from this distant monster, and the universe around it begins to blur into something stranger. Clusters of galaxies link into filaments. Filaments weave into walls, giant glowing structures that stretch for hundreds of millions of light years. Between them, vast, cold voids where almost nothing shines. For a long time, we thought that was the end of the story. Galaxies, clusters, filaments, voids, forever. But when we map the afterglow of the Big Bang itself, the cosmic microwave background, we find scars, cold spots and empty regions larger than our theories are comfortable with. Places like the Eridanus supervoid, billions of light years across, where there should have been hundreds of thousands of galaxies, and there are far fewer. Some scientists think these are just extreme patches of randomness. Others quietly wonder if they might be fingerprints of something beyond our universe entirely. Old collisions with other bubbles in a wider multiverse, now frozen into the sky as subtle bruises. We don't know. We may not know for a very long time. But that distant black hole Webb has found sits on that same grand tapestry. A single bright pin in a fabric we're only beginning to trace. Here on Earth, wrapped in our thin air and familiar gravity, it's easy to feel small in the face of all this. An ancient monster feeding in the dark, walls of galaxies, bottomless voids, maybe other universes pressing against the edges of our own. And yet, the light from that black hole traveled for more than 10 billion years just to brush the mirrors of a telescope we built on a tiny world around an ordinary star. It arrived here at exactly the right angle, in exactly the right moment, for a human mind to notice, measure, and whisper, "There you are. We see you." So as you drift toward sleep tonight, let that thought be your anchor. The universe is huge, yes, full of monsters and mysteries, but it is also readable. A story written in light, patiently waiting for us to learn the language. Somewhere beyond the known cosmos, an enormous black hole still feeds in the dark. And here, on a quiet planet in a small spiral arm, you are listening to its echo. Rest now, traveler. The universe is vast. We'll explore a little more of it when you wake. Planet 9 is basically the universe's biggest maybe. On paper, it explains a lot. In reality, almost everything about it feels Here's a fresh, original take you can use for Galactic Briefing based on that transcript. Same facts, completely rephrased and reorganized. 1. Big picture summary for your own notes. Key points the video covers. Andromeda's visible stellar disk is about 220,000 light-years across, roughly 3 times larger than old textbook values. It contains around 1 trillion stars, with an extended faint outer disk revealed by measuring star motions, not just brightness. Andromeda sits inside a huge, gaseous halo, circumgalactic medium, extending up to approximately 2 million light-years in some directions. That halo is extremely thin gas, less than 1 atom per 10 centimeters cubed. It's rich in heavy elements, oxygen, carbon, silicon, iron, blown out by billions of supernovae. It's structured in 2 main shells, an inner turbulent shell around 0.5 million light-years and a smoother, hotter outer shell around 0.5 to 2 million light-years. The halo's total gas mass is at least half the mass of all the stars in Andromeda. Andromeda and the Milky Way each have massive halos that already overlap, so their outer atmospheres are mixing right now. Andromeda is approaching us at 110 kilometers per second, but new simulations suggest the future is uncertain. Roughly coin flip odds of a full merger, depending on details like tangential motion and the influence of smaller galaxies, Triangulum, Large Magellanic Cloud. If they do merge, the end product is likely a huge elliptical galaxy, Milkomeda, with little new star formation and a merged supermassive black hole. 2. New YouTube title ideas. Pick or tweak. Andromeda is already touching the Milky Way, just not how you think. We were wrong about Andromeda's size. Here's the real monster next door. The invisible edge of Andromeda, a galaxy that reaches halfway to us. Andromeda's hidden halo, the largest thing in Earth's night sky.
Title idea. Light years, the cosmic distances our brains can't handle. Script. Cold open. Have you ever heard someone say, "This galaxy is millions of light years away," and just nodded politely? We all pretend we know what that means, But if you really follow that idea all the way down, what a light year actually is, what it means for travel, communication, and our future in the universe, it completely scrambles your sense of reality. Tonight on Galactic Briefing, we're going to unpack the light year, why astronomers had to invent it, what it tells us about our cosmic neighborhood, and how it quietly proves that the universe is both beautiful and brutally out of reach. And I promise, after this video, you will never look at the night sky the same way again. Beat. If you like deep dives into space, cosmology, and the weird limits of physics, consider subscribing. It helps a lot more than you think. All right, let's stretch your sense of distance until it breaks. 1. Distances our brains can handle. Let's start small, on Earth, where distance still means something. You know what a kilometer feels like. It's about a 10-12-minute walk. You can picture the route, a few corners, maybe a traffic light, your favorite cafe. 5 kilometers? That's a short drive, a quick bike ride, or a decent jog. You can plan that without thinking. 200 kilometers? That's a road trip. You think about gas, snacks, maybe a bathroom break. It's still human scale. You can experience that distance in a single day. Even the 40,000 kilometers around Earth's equator, while huge, is still conceptually manageable. In theory, planes can circle it, ships can sail around it. It's big, but it's not incomprehensible. Our brains evolved for this range. How far is the river? Can we reach that valley before sunset? Distances that matter to feet, horses, and cars. And then we leave Earth. 2. Where kilometers start to fail. The moon is about 348,000 kilometers away. Now we're already outside what your intuition can handle. You can't walk it, drive it, or even really visualize it. There's no scenery, no gas stations, just empty space and a very, very long line. Apollo astronauts took about 3 days to get there, traveling at roughly 11 kilometers per second. That's about 400 times faster than highway driving, for 3 straight days, just to touch the thing you can see with your naked eye. Already, kilometers are starting to feel clumsy. Then you hit the sun, about 150 million kilometers away. 150 million. You can say the number, but does it mean anything inside your head? Probably not. It's just huge. If you tried to cross that distance at Apollo speeds, you'd be traveling for months. And yet the sun is still local. It's our own star. When we move from planets to other stars, kilometers simply crumble as a useful unit. 3. Why astronomers switched to light. So astronomers pulled a clever trick. Instead of asking, how many kilometers away is that star? They ask, how far can light get in a certain amount of time? Because light is special. It travels at about 300,000 kilometers every second. It's the fastest thing in the universe. And as far as we know, nothing with mass can outrun it. So a light year isn't a measure of time. It's a measure of distance. 1 light year equals the distance light travels in 1 year. If you do the math, 300,000 kilometers per second times 60 times 60 times 24 times 365, you get about 9.46 trillion kilometers. So when you hear 1 light year, think a beam of light sprinting at the cosmic speed limit for a full year. And that's how far it gets. That's the unit astronomers use to measure the distance between stars. Not because they're being dramatic, because nothing smaller works. 4. Climbing the light ladder. Let's build up to a light year step by step. Think of it as a light ladder. 1 light second. Distance approximately 300,000 kilometers, roughly from Earth to the moon and most of the way back. When astronauts were on the moon, their radio messages took a little over 1 second to reach Earth. 1 light minute. Distance approximately 18 million kilometers. The sun is about 8 light minutes away. When you look at the sun, with proper protection please, you're seeing it as it was 8 minutes ago. 1 light hour. Distance about 1.08 billion kilometers. Planets like Saturn can be around a light hour or more from us. Signals from spacecraft out there take over an hour to reach Earth. 1 light day. Distance about 25.9 billion kilometers. Voyager 1, humanity's most distant probe, has been flying since 1977 and is still less than a light day from the sun. 1 light week. Distance approximately 181 billion kilometers. Now you're well beyond the planets out into deep space. The sun would just look like a bright star. 1 light year. Stack 365 of those light days together, you get that colossal 9.46 trillion kilometers. You can see how quickly the numbers explode. We started from moon in 1.3 seconds, and in a few steps, we're at distances where entire planetary systems vanish into a point. 5. Our nearest neighbor star. The nearest star beyond the sun is Proxima Centauri, about 4.24 light years away. In kilometers, that's roughly 40 trillion kilometers. If you tried to go there using our fastest spacecraft to date, something like the Parker Solar Probe at its top speeds, it would still take on the order of thousands of years. Think about that. All of recorded human history fits inside the last few thousand years, and that's how long you'd be coasting in a metal can just to reach the closest star. That's what a short distance in interstellar terms looks like. 6. Light years equal distance and time. Here's where things get really wild. Because light has a finite speed, distance and time are welded together. When we say a star is X light years away, we're also saying we see it as it was X years ago. Some examples. The sun, 8 light minutes away. You're always watching the sun with an 8-minute delay. Sirius, the brightest star in our night sky, about 8.6 light years away. You see it as it was 8.6 years in the past. Vega, about 25 light years. If you're 25, the light hitting your eyes tonight left the star the year you were born. Betelgeuse, about 550 light years. Its light started traveling toward us in the late 1400s during the Renaissance. And here's the spooky part. Betelgeuse is a massive, unstable star nearing the end of its life. It could explode as a supernova any time in the next 100,000 years. For all we know, it might have already exploded centuries ago. We just haven't seen it yet because the news is still in transit at light speed. So some of the stars you see in the sky might literally be ghosts, images of things that have already changed or died. 7. The Milky Way in light years. Now, zoom out to our galaxy. The Milky Way is roughly 100,000 light years across. Our sun is about 26,000 light years from the galaxy's center. That means light leaving the center of the galaxy when humans were still using stone tools is only arriving around now. To cross the galaxy at light speed, if you could, would take 100,000 years. Remember, modern humans have existed for about 300,000 years as a species, so a single light speed trip across the galaxy would take about 1/3 of our species' entire existence. And the Milky Way is just one galaxy among a lot. The observable universe stretches about 93 billion light years across and contains trillions of galaxies.
At this scale, even a distance of 100 light years, which already feels enormous, is tiny, like a little neighborhood block. 8. Why you can't just go faster. At this point, you might be thinking, okay, fine, light is fast, but can't we just build a ship that goes like 10 times faster than light, 100 times faster? Short answer, no, at least not according to the physics we currently know. Einstein's theory of relativity tells us, as you accelerate closer to light speed, time slows down for you relative to people who stay behind. Your effective inertia.
Here's a fresh, original script you can use for Galactic Briefing, built from the ideas in that transcript, but completely restructured and reworded, with a stronger focus on Planet 9 and why it feels wrong in every possible way. You can tweak length by speeding up or slowing narration, but this is roughly a 12 to 15-minute video. Title ideas. Scientists may have found Planet 9, but something is seriously off. The Planet 9 candidate that feels wrong in every way. Planet 9, the hidden world that shouldn't exist. YouTube script. Planet 9 candidate that feels wrong in every way. Channel note. Narration is written in your calm, curious, documentary voice. 000. Cold open. Imagine a giant icy planet, 10 times the mass of Earth, taking up to 20,000 years to orbit the sun just once. We've never seen it, but something out there is tugging on the outer solar system, and the numbers refuse to behave. Some astronomers are now convinced they've narrowed down a real candidate for Planet 9. The problem? If their models are right, this world shouldn't exist where it is, and maybe not at all. Welcome to Galactic Briefing. Today, why Planet 9 might be real, why it might be totally wrong, and how a future telescope could end the mystery once and for all. 0045 Segment 1. We've found invisible planets before. For most of human history, the solar system ended with Saturn. Then in 1781, William Herschel pointed his telescope at a faint, bluish object he thought was a star and accidentally discovered Uranus. That was our first taste of something big. Planets can hide in plain sight. A few decades later, astronomers noticed that Uranus's orbit wasn't quite right. It moved as if some unseen mass was pulling on it. Instead of guessing wildly, mathematicians used gravity and equations to predict where that missing planet should be. In 1846, telescopes turned to that patch of sky, and Neptune appeared almost exactly where the math said it would be. So the idea behind Planet 9 isn't crazy. We've used gravitational weirdness to predict a hidden planet before, and it worked. But it also failed spectacularly. 2-minute Segment 2. The planet that never was, Vulcan. In the 19th century, another small world started misbehaving, Mercury. Its orbit shifted in a way that Newtonian gravity couldn't fully explain. So a French astronomer, Urbain Le Verrier, proposed a new planet even closer to the Sun, inside Mercury's orbit. He called it Vulcan. People searched everywhere, during solar eclipses, through telescopes, staring into the blinding region near the Sun. Some even claimed to see it. But Vulcan was never confirmed. The problem wasn't the observations, it was the theory of gravity they were using. Einstein's general relativity later showed that Mercury's strange orbit was perfectly normal if you account for the Sun curving space-time. No hidden planet was needed. Vulcan evaporated into history. That story haunts the Planet 9 debate. Are we looking at a real planet or at the limits of our current understanding of gravity and the outer solar system? 3 minutes, 10 seconds, Segment 3. The anomaly in the dark. Jump to the 21st century. Far beyond Neptune, in the icy Kuiper Belt, astronomers began mapping hundreds of small frozen worlds, dwarf planets, comets, and other leftovers from the birth of the solar system. A strange pattern appeared.
The 6 most distant objects didn't orbit randomly. Their stretched out paths in space were elliptical in a similar way, clustered in one general direction, and tilted by roughly the same angle compared to the orbits of the 8 known planets. The odds of that happening by pure chance were tiny, fraction of a percent tiny. 2 researchers, Konstantin Batygin and Mike Brown, asked a simple question. If we assume there's another planet out there, can it naturally produce this pattern? Their simulations suggested yes. To explain those weird orbits, you'd need something like a planet 5 to 10 times Earth's mass, on a huge elongated orbit maybe 400 to 800 times farther from the Sun than Earth, taking up to 20,000 years to complete a single year. They called it Planet 9. Others called it Planet X. Pluto, unfortunately, was still not invited back into the Planet Club. 4 minutes 30 seconds, segment 4. The case for Planet 9. As more distant objects were discovered, some of them also seemed to line up in this strange way. The Planet 9 model got more detailed. It could shepherd these icy objects into similar orbits. It might explain why some bodies are tilted so far out of the solar system's usual plane. It could even generate rare, highly elongated orbits like those of Sedna and other detached objects that never come close to the giant planets. Later, another team tried a different approach. Instead of just looking at the shapes of the orbits, they studied where these distant objects cross the plane of the solar system, their nodes. If something massive lurks far away, it should influence where those crossing points cluster. Their calculations suggested the best place to put Planet 9 was 300 to 400 times farther from the Sun than Earth, still unimaginably distant, but closer than early guesses. Some studies even claim that when you factor in more detailed orbital behavior, Planet 9 might be responsible for the strange motions with 99% confidence rather than mere coincidence. On paper, it's an elegant solution. But why does it feel wrong? 5 minutes 50 seconds, segment 5. Why Planet 9 feels wrong in every way. There are a few big problems. 1. We still haven't seen it. A planet 10 times more massive than Earth is not subtle. Yes, it would be extremely faint and cold at hundreds of astronomical units away. But multiple deep sky surveys have scanned large swaths of the sky at visible and infrared wavelengths and found nothing obvious. A project in Hawaii, the Pan-STARRS survey, has already ruled out about 3/4 of the most likely places Planet 9 could be hiding. That still leaves a chunk of sky, but every non-detection tightens the noose. 2. The data is thin and possibly biased. Those aligned distant objects are a very small sample, and they were mostly found by surveys that only cover certain regions of the sky at certain times with certain brightness limits. If you only look in a few directions, you'll mostly find objects in those directions. Some astronomers argue that once you properly account for all the observational biases, the statistical evidence for Planet 9 drops dramatically. Maybe the orbits just look special because our search pattern is special. 3. Formation is a nightmare. How do you even make a planet like this? It's too far from the Sun for the usual planet building process to work efficiently. If it started closer in and was kicked outward by Jupiter or Saturn, why wasn't it ejected into interstellar space entirely? And if it was captured from another star system passing by billions of years ago, that requires a very specific, unlikely cosmic choreography. In other words, Planet 9 solves one puzzle, but creates several more. 7 minutes 20 seconds, segment 6. Alternative explanations, black holes and broken gravity. If Planet 9 feels wrong, what else could be causing the strange orbits in the outer solar system? Option A, a swarm instead of a giant. Maybe there's no single hidden planet. Instead, a collective mass of many smaller objects, dwarf planets, icy bodies, maybe an undiscovered Mars-sized world, could together nudge orbits into the pattern we see. Think of it as a crowd pushing, not one big bully. Option B, a tiny black hole. Some researchers have floated a wild idea. What if Planet 9 is actually a primordial black hole, perhaps only a few centimeters across, but with the mass of a planet? It would be almost invisible. No light, no reflection, just gravity. It's a long shot, but mathematically, it can mimic a planet's pull without emitting any light. Option C. Gravity itself is wrong in the outskirts. Another camp thinks we might be hitting the edge of our gravity theories again, like with Vulcan and Mercury. A framework called Modified Newtonian Dynamics, or MOND, suggests that at extremely low accelerations, like those far out in the solar system, gravity might behave differently than we expect. In that view, strange Kuiper belt orbits might not need a hidden planet at all. They might be telling us that the Milky Way's gravitational field is subtly influencing our outer solar system in a way our models don't fully capture. Even supporters of these ideas admit it's early, messy, and far from settled. But they show why Planet 9, as elegant as it is, doesn't have a monopoly on explanations. 9 Minutes, Segment 7. The Moons as Flashlights. One of the more creative twists in the Planet 9 saga comes from
Cold open, hook. Imagine zooming out from the Milky Way, past our neighboring galaxies, past giant clusters and filaments, until you reach a huge, dark bubble of almost nothing. And right in the middle of that cosmic emptiness is a tiny blue galaxy that should not be doing what it's doing. No neighbors, no collisions, no mergers. And yet, this lonely dwarf galaxy is suddenly bursting with new stars. How is that even possible? Beat. Today, we're going into the cosmic void to visit a galaxy that might be showing us how parts of the universe are still being built, 13 billion years late. Show channel logo or intro animation. Main script. Hello and welcome back to Galactic Briefing. Today we're talking about a galaxy that lives in one of the emptiest places in the universe, and somehow it woke up. The cosmic web and its dark bubbles. If you could pull way back from the universe and see everything at once, it wouldn't look like a random scattering of galaxies. It would look like a 3D spider web. Bright knots where galaxy clusters live. Long glowing filaments connecting those clusters. And in between, huge dark bubbles of almost nothing called cosmic voids. These voids are enormous, tens to hundreds of millions of light years across, with matter density maybe 1/10 the cosmic average. They're not perfectly empty, but compared to the crowded city life along the filaments, a void is the deep countryside of the cosmos. And here's a fun twist. Our own Milky Way sits right next to one of these regions, called the local void. So we live just off the edge of a giant patch of nothing. A galaxy inside the void. Now, inside one of these underpopulated regions, astronomers found an odd little galaxy called NGC 6789. It's about 12 million light years away. Small. Blue. And classified as a blue compact dwarf galaxy. Dwarf because it has much less mass than a big spiral like the Milky Way. Blue compact because a lot of its light is coming from young, hot blue stars packed into a tiny central region. From a distance, it just looks like a fuzzy blue blob. Nothing fancy, but its address is what makes it special. NGC 6789 lives inside a cosmic void, essentially right in the middle of nowhere. And that's where the problem starts. Why this is a cosmic paradox. Galaxies usually grow and evolve by interacting with their neighbors. They tug on each other with gravity, they collide and merge, they rip gas and stars out of each other's disks.
All that chaos compresses gas, creates overdense clumps, and triggers new star formation. But galaxies in a void? They're supposed to be the opposite. Isolated, undisturbed, quiet fossil relics from the early universe. That was the expectation. Void galaxies should be old, faded, and sleepy. NGC 6789 didn't get that memo. A young heart in an old, empty place. When astronomers looked more closely at NGC 6789, they found something surprising. About 4% of all the stars in this galaxy, around 100 million solar masses worth, formed in just the last 600 million years. On cosmic timescales, that is very recent. So this lonely void galaxy has had a vigorous starburst phase without any neighbors to slam into. And that raises one big question. How did it get the gas to form all those stars if it lives in the middle of nothing? Looking for the usual suspects and finding nothing. To solve this, astronomers did deep imaging of NGC 6789, pushing their telescopes to see very faint structures far beyond the bright central region. They were hunting for tidal tails, long streaks of stars pulled out during a merger, faint stellar streams, leftover debris from smaller galaxies that got eaten, any sign at all that NGC 6789 had collided with or swallowed something in the past billion years. If there had been a recent merger big enough to feed a starburst, it should have left a mess. Warped outer regions, broken symmetry, streams of stars wrapping around the galaxy. Instead, they found a smooth, undisturbed outer halo with a redder, older stellar population. No tidal tails, no big streams, only a tiny amount of leftover debris, way too little to explain all that new star formation. So, no crashes, no flybys, no obvious fuel tanker galaxy. And yet, the starburst happened. The hidden pipeline from the void. If the gas didn't come from another galaxy, then the only remaining option is more radical. The fuel for these new stars came directly from the cosmic void. That sounds wrong at first. Void equals empty, right? But remember, voids are low density, not perfectly empty. They can still contain thin wisps of hydrogen, faint threads of material like ghost filaments connecting to the main cosmic leb. Astronomers call this idea cold gas accretion. Pristine, very low metallicity gas that has never been through a star, slowly streaming in from intergalactic space, quietly raining down onto a galaxy's halo and disk. Over time, that gas can build up, become dense in the center, and suddenly ignite a burst of star formation, even in a galaxy that's totally isolated. NGC 6789 seems to be one of these cases. Chemical clues. Ancient gas, new stars. How do we know the gas is pristine and not recycled from old stars? That's where chemistry comes in. Stars forge heavy elements like oxygen, nitrogen, and metals in their cores and supernova. So, gas that's been through multiple generations of stars gets metal-rich. But in NGC 6789, the gas is metal-poor, low in oxygen overall. But the nitrogen to oxygen ratio is consistent with what you'd expect after dilution by fresh, untouched gas. In simple terms, it looks like a large amount of very ancient, almost primordial gas mixed in with the galaxy's existing material. That's exactly what you'd expect if a thin stream or cloud of void gas slowly flowed in, blended with the galaxy's interstellar medium, then collapsed and formed a surge of new stars. So, the story might be, for over 13 billion years, some patch of hydrogen has been drifting in the emptiness of a cosmic void, until it finally fell into this tiny galaxy and lit it up. Another void galaxy with the same problem. NGC 6789 is not completely alone in this behavior. Astronomers have also studied another void galaxy called VGS 12. It lives inside a void as well. It has a weird polar gas disk, a giant ring of gas orbiting at right angles to its main stellar disk. That gas is also metal poor, and its chemistry suggests recent dilution by pristine material. In this galaxy, we can actually see the extended gas structures, giving very strong evidence that cold gas is being accreted right now. So now we've got multiple galaxies and voids that have no big mergers, show fresh star formation, and carry the chemical fingerprint of ancient untouched gas finally joining the party. What this means for galaxy evolution. This all points to something pretty important. Galaxies don't only grow by smashing into each other. Yes, mergers are still a big deal in crowded environments, but in quiet, isolated regions like cosmic voids, there can be a second growth channel. Slow, steady fuel supply from the invisible filaments and wisps of the cosmic web, feeding galaxies with cold gas even billions of years after the Big Bang. And that means some galaxies and voids might be late bloomers, forming stars much later than their cousins in crowded clusters. They can look younger today, even though they've been sitting there since the early universe. It's like having a town that didn't get electricity last year. The universe is old, that the lights just came on. A window into the early universe. What makes NGC 6789 and its void cousins so valuable is that they may be giving us a time machine. The gas falling in today has been untouched since the early universe. The way it forms stars in a small, isolated galaxy may resemble what happened in the very first galaxies to light up. So by studying these lonely, delayed galaxies, we might be seeing primordial gas finally being used, early-style star formation happening in the modern universe, all thanks to a galaxy living alone, in the middle of almost nothing. Outro. So, in summary, cosmic voids aren't perfectly empty. They hide thin streams of ancient gas that can still build galaxies. NGC 6789 is a void galaxy that suddenly started forming stars with no mergers, no collisions, and no obvious trigger, except for a hidden cosmic pipeline feeding it pristine fuel straight from the void. And that means the cosmic web is still quietly shaping. The moon is the closest world to Earth, just 384,000 kilometers away. We can see its craters, dark plains, and bright highlands with the naked eye. Humans have even walked on it, brought back hundreds of kilograms of rock and soil, and studied it for decades. And yet, we are still only beginning to understand it. One of the biggest mysteries? Water. Because if humanity ever wants to live on the moon for months, years, or even generations, water isn't optional. It's the first requirement. In this video-style summary, we're going to travel through 4 big stories: the long, dramatic hunt for water on the moon, the violent reality of earthquakes and quakes on other worlds, the shocking Starliner failure and the rescue mission that humiliated Boeing, and finally, the rise of Euclid, the space telescope hunting the dark side of the universe. You don't need to watch the original video. By the end of this narration, you'll know the whole story. 1. Water on the moon, from illusion to discovery. For centuries, astronomers stared at the moon's dark blotches and guessed at their nature. Back in 1645, the Dutch astronomer Michael van Langren published one of the first lunar maps and called those dark areas Maria, Latin for seas. People genuinely believed the moon had oceans. Later, even Leonardo da Vinci speculated that the moon's surface was covered by water, reflecting sunlight like Earth's oceans. He thought waves on this lunar sea scattered the light, making the moon glow softly instead of blazing like the sun. We now know those seas are not water at all. They are dark lava plains frozen from ancient volcanic eruptions. The word Maria survived, but the idea of lunar oceans died. By the late 1800s, American astronomer William Pickering carefully measured the moon and concluded no clouds, no real atmosphere, and therefore no liquid water on the surface. For decades, science treated the moon as a completely dry world. If any water ever touched the surface, it was assumed it would instantly evaporate into space. Then came the Apollo era. Between 1969 and 1972, astronauts walked on the moon, scooped up rocks and soil, and brought them back to Earth. When those samples were first examined, scientists found essentially no water. Any tiny trace was written off as contamination from Earth. The verdict seems clear. The moon is bone dry. The idea of lunar water was pushed aside, almost forgotten. A robot changes the story. In 1976, the Soviet robotic mission Luna 24 landed on the moon, drilled nearly 2 meters into the surface, and sent about 170 grams of soil back home. When scientists analyzed those samples, they found a surprise. About 0.1% of the sample's mass was water. The deeper the sample, the more water it contained. It was the first direct measurement of water in lunar soil. And yet, once again, many dismissed it as contamination. The mystery of lunar water remained unresolved. Clementine and the shadowed craters. In 1994, a U.S. military mission called Clementine orbited the moon to map its minerals. But Clementine did something more. It used radar to probe the permanently shadowed craters at the lunar South Pole, places where sunlight never, ever reaches. The experiment beamed radio waves into these dark regions and listened to the echoes with giant antennas on Earth. The signal looked exactly like what you'd expect from a surface covered in ice, not bare rock. For the first time, scientists had strong evidence that water ice might be hiding in eternal darkness at the poles. These regions are unimaginably cold, around minus 230 degrees Celsius or colder, cold enough to trap water ice for billions of years. That discovery ignited a new wave of missions. Lunar Prospector, Kaguya, and failed impacts. In 1998, NASA's Lunar Prospector orbited the moon and mapped large amounts of hydrogen near both poles. Hydrogen could mean water ice, but it could also mean hydrogen bound in minerals, like OH groups. To test this, at the end of its mission in 1999, Lunar Prospector was deliberately crashed into a crater near the South Pole. Scientists hoped the impact would throw up a plume of dust and ice that telescopes on Earth could analyze. But they saw no clear signal of water. In 2007, Japan's Kaguya orbiter repeated a similar idea. It also ended its mission by crashing into the moon, hoping to reveal hidden water. Again, no definitive detection. The moon kept its secret. The Apollo samples speak again. In 2008, with better technology, scientists at Brown University took a fresh look at the old Apollo samples, this time focusing on tiny volcanic glass beads formed in ancient lunar eruptions. Inside these glassy beads, they found hydrogen. This was huge. It meant that water wasn't only coming from the outside, like comets. Some of it came from inside the moon itself. In other words, the moon has contained water since its early history, possibly since its formation. The dry moon idea was starting to crack. Chandrayaan-1 and the first confirmations. In 2008, India launched its first lunar mission, Chandrayaan-1. This spacecraft carried multiple instruments, including a NASA infrared spectrometer to detect water or hydroxide on the surface, a moon impact probe designed to slam into the lunar South Pole, analyze the plume, and look for water vapor. As the impact probe descended, it transmitted data back to the orbiter. In that data, scientists finally saw the clear spectral fingerprints of water.
Chandrayaan-1 also helped identify over 40 permanently shadowed craters near the North Pole that could store around 600 million tons of water ice. The moon was no longer dry. It was quietly wet in the coldest, darkest places. LCROS, LRO, and the final proof. In 2009, NASA launched two more key missions. LCROS, a dedicated impactor, LRO, the Lunar Reconnaissance Orbiter. LCROS first crashed a heavy spent rocket stage into a shadowed crater near the South Pole, then flew through the debris plume itself before crashing in turn. LRO stayed in orbit watching and measuring. This time, the evidence was undeniable. The plume contained water ice, particles, along with other volatiles. Water ice does exist in permanently shadowed regions of the moon. Over the next decade, more data followed. In 2018, scientists used Chandrayaan-1 data to directly map discrete patches of ice at both poles. In 2020, NASA's Airborne Observatory, SOFIA, detected molecular water, H2O, on a sunlit region of the moon, at Clavius Crater, at a concentration of about 340 grams of water per cubic meter of soil, roughly the equivalent of a small bottle of water per cubic meter. In 2023, the first detailed water map of the moon's south polar region was released, guiding future missions like NASA's Artemis program and the Viper rover. Today, estimates suggest there may be up to 600 billion kilograms of water ice on the moon. Not as abundant as on Earth, but more than enough to transform lunar exploration. The harsh reality of using that water, knowing the water is there, is only the first step. Getting to it is another challenge. The moon has brutal temperature extremes. In sunlit regions, up to 127 degrees Celsius. In darkness, down to minus 173 degrees Celsius. In the darkest polar craters, around minus 250 degrees Celsius, colder than Uranus or Neptune. These shadowed cold traps might be perfect natural freezers for water and organic compounds, but they are a nightmare for engineering. How do you land safely in such deep shadows? How do you operate machinery at temperatures hundreds of degrees below freezing? How do you keep astronauts alive there? Despite this, major space powers are already eyeing these regions. The United States plans to build a permanent base near the South Pole by around 2030 under the Artemis program. China, together with Russia and other partners, are planning a robotic research station at the lunar South Pole, using missions like Chang'e 6, 7, and 8. The race is on. Who will be the first to step into the eternal darkness of the lunar poles? Who will tap the moon's hidden reservoirs of ice? And who will claim the most valuable real estate beyond Earth? For now, those answers are still in the future. 2. Earthquakes and quakes across the solar system. Let's leave the moon for a moment and come back home to something that feels much more familiar and terrifying: earthquakes. How an earthquake really works. Imagine Earth's crust as a jigsaw puzzle of giant slabs called tectonic plates. These plates float on top of the hot, slowly flowing mantle beneath. But they don't slide